You probably think the most dangerous place in the universe is inside a black hole. Reasonable guess. It is also wrong. Long before you reach one, the universe can sandblast you with glass, boil oceans made of rock, dismantle atoms with magnetism, or sterilize a planet from thousands of light years away. And the final threat is not a place that destroys you. It is a place where the laws that make you possible may no longer exist. So let us cross 9 cosmic danger zones, beginning with a world that looks disturbingly familiar. HD 189733b is a deep cobalt blue, almost like Earth seen from space. But there are no blue oceans beneath those clouds. This planet is a hot Jupiter, a gas giant, orbiting so close to its star that its atmosphere is heated above 1,000 degrees Celsius. Its blue color probably comes from a haze containing tiny silicate particles, the same basic family of material found in glass. Winds may race around the planet at more than 7,000 kilometers per hour. If those particles condense, the result could resemble glass rain driven almost sideways through the atmosphere. Calling it rain feels generous. It would be closer to flying through a supersonic industrial sandblaster. HD 189733b is beautiful in exactly the way a blue flame is beautiful from somewhere else. If glass weather seems excessive, K2141b removes the glass and melts the rest of the planet. This rocky world circles its star in less than 1 Earth day. It is probably tidally locked, with one hemisphere trapped beneath permanent daylight and the other facing permanent night. On the day side, temperatures may climb beyond 2,500 degrees Celsius. Rock does not merely melt there, some of it vaporizes. Models suggest K2141b could have a magma ocean, feeding a thin atmosphere made partly from sodium, silicon monoxide, and other components of stone. Winds carry that rock vapor toward cooler regions, where it may condense and flow back toward the dayside. Earth has a water cycle. K2141b may have a rock cycle. Clouds, precipitation, currents, and an ocean are all present in the proposal. The universe has simply replaced the water with geology and declared the renovation complete. Those first 2 worlds destroy familiar weather. The next destination destroys familiar matter. A neutron star forms when the core of a massive dying star collapses. More mass than our sun can be compressed into a sphere roughly 20 to 25 kilometers wide. That is not a small star. It is a stellar mass packed into the size of a city. The gravity at its surface may be around 100 billion times stronger than gravity on Earth. A tiny amount of its material, if somehow kept under neutron star pressure, would have the mass of a mountain. But you would never arrive carrying a sample jar. As you approached, the difference in gravity between the near and far sides of your body would stretch and accelerate you downward. Then you would strike the crust at an appreciable fraction of light speed. Even the landscape has been bullied flat. Under such gravity, a neutron star mountain may rise only centimeters or perhaps meters, depending on the crust. On Earth, we climb mountains. On a neutron star, gravity has already dealt with that nonsense. Now take that collapsed star and give it the strongest magnetic field known in nature. You have a Magnetar. SGR 1806-20 is one example. Its surface magnetic field is estimated at around 200 billion Tesla or more. Earth's field is measured in millionths of a Tesla. Close to a Magnetar. This is not the sort of magnetism that steals your keys. It can distort electron clouds, disrupt chemical bonds, and eventually make atoms themselves behave in deeply inconvenient ways. In 2004, SGR 1806-20 released a giant flare. It lasted only a fraction of a second, Yet it affected Earth's upper atmosphere from tens of thousands of light-years away. Place a flare like that within about 10 light-years, and it could severely damage our ozone layer. Place yourself within roughly 1,000 kilometers of the Magnetar, and the field alone may begin dismantling ordinary matter. There is no useful survival advice here. Do not approach the Magnetar is less a strategy than a basic reading of the room. So far, the danger has been local. One traveler chooses a terrible destination and receives a very short review period. A supernova can threaten an entire living world. When a massive star reaches the end of its fuel, its core can collapse and its outer layers explode into space. The visible blast is spectacular. But for a nearby planet, the more serious problem may be high-energy radiation and cosmic rays. These can alter atmospheric chemistry, weaken the ozone layer, and allow more harmful ultraviolet radiation from the planet's own star to reach the surface. Betelgeuse will eventually explode as a supernova. It is so large that, placed at the center of our solar system, its outer layers would extend beyond Mars and perhaps toward Jupiter. Fortunately, it is roughly 600 light-years away. That is close enough for an extraordinary show, and far enough that Earth is not expected to become part of it. To pose a major biological threat, a supernova would generally need to occur within tens of light-years, although the exact danger depends on the explosion. In other words, Betelgeuse is dramatic, not homicidal. The night sky is allowed to have boundaries. But some stellar deaths concentrate their violence instead of throwing it equally in every direction. A gamma-ray burst can fire narrow beams of high-energy radiation from a collapsing massive star or the merger of compact objects. For a planet caught inside one of those beams, distance becomes a deceptive comfort. A sufficiently powerful burst within a few thousand light-years could break apart molecules high in the atmosphere and remove a substantial fraction of the ozone layer. The burst itself might last seconds. The resulting increase in solar ultraviolet radiation could persist for years, damaging ecosystems long after the source had faded. There would be no telescope warning you that the beam was almost here. Gamma rays travel at light speed. The first information about the event arrives with the event. Space occasionally sends notifications and consequences in the same package. The danger now reaches across the galaxy. Near an active supermassive black hole, it can reshape a galaxy's environment. A black hole is dark, but a feeding black hole can become surrounded by an accretion disk. Gas and dust spiraling inward, colliding and heating to extreme temperatures. Magnetic fields can also launch narrow jets of particles moving close to light speed. When this engine is powerful enough, we see a quasar. 3C273 was the first quasar, whose enormous distance helped reveal what these strange points of light really were. Its central black hole is hidden inside a region so luminous that it can outshine the combined stars of an entire galaxy. The event horizon is not the only hazard. Long before crossing it, radiation from the disk could sterilize exposed worlds, while tidal forces and high-speed material turn the surrounding region into a machine with no safe moving parts. The darkest object in the system creates one of the brightest environments in existence. The universe enjoys that kind of joke, although enjoys may be assigning it too much personality. At least an active black hole advertises itself. A lone black hole may travel through the galaxy with no bright companion, no glowing disk, and almost no direct light at all. Astronomers search for these isolated black holes using gravitational microlensing. When one passes in front of a distant star, its gravity bends and magnifies the star's light. Precise observations can also reveal a tiny shift in the star's apparent position. The black hole becomes visible only through what it does to something behind it. Candidates have been identified. Although measuring their masses is difficult, and some classifications remain debated. There may be many isolated stellar remnants moving through the Milky Way. That does not mean one is secretly racing toward Earth. Space is enormous. Close encounters are extraordinarily unlikely, and black holes do not roam like vacuum cleaners, searching for planets. Still, the image is unsettling. Several suns' worth of mass, almost completely dark, announced by a background star appearing to move incorrectly. Every destination so far is dangerous because the laws of physics work exactly as expected. Gravity pulls, radiation ionizes, magnetic fields act on charged particles. The last possibility is different. It asks whether the rules themselves are permanent. In quantum physics, empty space is not truly empty. Fields exist throughout the universe, including the Higgs field, which is connected to the masses of fundamental particles. Measurements of the Higgs boson and the top quark suggest that our present vacuum may be metastable. That means it could resemble a ball resting in a shallow valley, while a deeper valley exists somewhere beyond an energy barrier. Metastable does not mean unstable tomorrow. Calculations can give the vacuum a lifetime vastly longer than the universe has existed, and unknown physics could change the conclusion entirely. No vacuum decay event has ever been observed. But if a quantum transition somehow created a bubble of lower energy vacuum, the physical conditions inside it could be different from those outside. The bubble would expand at nearly the speed of light. Atoms, chemistry, and matter as we know them might not survive the altered rules. No warning could outrun the boundary, because information cannot travel faster than light. This is not a prediction that reality is about to end. It is a theoretical possibility, and particle accelerators are not expected to trigger it. Natural cosmic rays have produced higher energy collisions for billions of years, and the universe remains irritatingly present. The scariest places in the universe are not frightening because they are evil. They have no intention at all. A blue planet does not care that it resembles home. A magnetar does not know that its field can dismantle matter. A gamma-ray burst does not aim. We began by assuming the ultimate danger was inside a black hole. But the deeper lesson is less theatrical and more unsettling. The universe does not need to hide monsters in the dark. Given enough heat, gravity, energy, or time, the ordinary laws of nature are frightening enough.